Good morning, everyone. Now it's time to learn about X-ray circuit components and the different types of generators. We will look at a simplified diagram of an X-ray circuit and is intended to aid your understanding of the various components of the circuit and how they work together to produce and control X-rays. We will go over the various features of the X-ray circuit and the X-ray control panel. It is not necessary to memorize the circuits in detail, but have a baseline understanding.
The circuits help you to understand how three relatively complex electric circuits are integrated to produce X-rays. Because X-ray tubes may be damaged by improper use and are expensive to replace, we will go over guidelines for the safe operation of tubes and suggestions for prolonging tube life. The X-ray circuit is divided into three sections or subcircuits: the low-voltage circuit, the filament circuit, and the high-voltage circuit. Each circuit contains a specialty transformer. Now let's take a closer look at the diagram of an X-ray circuit. While looking at the diagram, please pause the video so that you can become familiar with the components. Each section is numbered and will aid in identifying the circuit parts. The low-voltage circuit is the subcircuit between the alternating current power supply, 1, and the primary input side of the high-voltage step-up transformer, 7. If you trace this circuit beginning at the AC power supply, you will note that current flows through several devices before reaching the primary side of the step-up transformer. From the transformer, it returns to the power source, forming an enclosed loop. With the exception of the step-up transformer, all of the devices in this subcircuit are actually located within the control console. The control console is the unit where the operator sets all of the exposure techniques, such as kilovolts peak, milliamperes, and exposure time. They include the main switch, 2, auto transformer, 3, kVp selectors, 4, exposure switch, 5, and exposure timer, 6. The AC power supply, 1, is wired into the building, providing electric power from the local power company. Most outpatient facilities have a 220 V power supply going into the X-ray room. Hospitals with more powerful equipment may have a larger supply. The main switch, 2, controls the power to the control console. Many of the components in this circuit operate at the standard 120 V. Although the power supply may be rated at 220 V, the actual voltage can vary as much as plus or minus 5%, depending on the demand for power in the building or the neighborhood. Small variations in the incoming line voltage may cause large variations in the kVp to the X-ray tube. For this reason, the incoming voltage is monitored and stabilized by a voltage compensator. The auto transformer, 3, is a single-coil transformer that serves three functions. It provides the means for kVp selection, it provides compensation for fluctuations in the incoming line voltage, and it supplies power to other parts of the X-ray circuit. The auto transformer's primary purpose is to vary the voltage to the primary side of the step-up transformer. This is accomplished by the kVp selector, 4, which is on the secondary output side of the auto transformer. The auto transformer varies the kVp to the tube by controlling the input to the step-up transformer. The exposure switch, 5, closes the circuit, allowing electric current to flow through the primary side of the step-up transformer. When this occurs, current is induced to flow through the secondary side of the transformer, creating voltage across the X-ray tube. As discussed earlier, this voltage causes the electron stream to flow across the tube, producing X-rays. The exposure timer, 6, is a device that terminates the exposure and is set by the operator on the control console.
The filament circuit is the sub-circuit of the main X-ray circuit shown as the lower portion of the diagram. This circuit is divided into two parts by the step-down transformer, 11 and 12. The primary purpose of the filament circuit is to supply a low current to heat the X-ray tube filament for thermionic emission of electrons. The filament circuit is activated anytime the operator adjusts the MA on the generator. The primary side of the circuit begins and ends with the contacts on the auto transformer, 9. Current in this circuit flows from the auto transformer through the MA selector, 10, and the primary side of the step-down transformer, 11, and back to the auto transformer. The secondary side begins and ends with the secondary side of the step-down transformer, 12, conducting current through the X-ray tube filament, 13. The step-down transformer reduces the voltage on the secondary side, providing an appropriate current to heat the filament. The MA selector, 10, controls amperage in the filament circuit. Because the current through this circuit controls filament heat, this setting determines the number of available electrons at the X-ray tube filament and thus determines the MA in the high-voltage circuit that includes the X-ray tube. The high-voltage circuit is the sub-circuit shown in the upper right portion of the diagram. This circuit begins and ends with the secondary side of the step-up transformer, 8. It includes the X-ray tube, 14, and the rectifier unit, 15. Current flows in the circuit only during an exposure. This is a dangerous circuit because of the very high voltage. The high voltage cables going to the X-ray tube are very thick because of their high insulation requirement. The step-up transformer is also referred to as the high voltage or high tension transformer. This transformer has a very high ratio of at least 500 to 1. For example, if the primary side of the step-up transformer receives 180 volts from the auto transformer, and the ratio is 500 to 1, the voltage induced on the secondary side will be 90,000 volts, or 90 kVp. The primary purpose of the high-voltage circuit is to supply the X-ray tube with voltage high enough to create X-rays. The auto transformer, step-down transformer, and high-voltage transformer are all located in a tank near the X-ray machine. Oil surrounds the transformers inside the tank for heat dissipation.
Now let's talk about rectification, the process of changing alternating current into direct current so it flows in one direction only. The primary purpose of the rectifier unit is to change the alternating current, AC, into direct current, DC. The process of rectification prepares the current for X-ray production by ensuring that it flows in the right direction, in this case from the filament to the target. There are 3 ways in which current is rectified: self-rectification, half-wave rectification, and full-wave rectification. Self-rectification was an inefficient form of rectification and is no longer used. Half-wave rectification and full-wave rectification are described next. With half-wave rectification, AC electrical current travels in the copper wire as a sine wave. It moves in a pulsating manner from positive to negative at a rate of 60 pulses, or waves, per second and is stated as 60 Hz. Rectifiers use diodes to convert the circuit from AC to DC. A diode is an electronic device that permits current to flow in one direction only. 2 diodes are used in half-wave rectification. In half-wave rectification, the negative phase of the electric cycle is totally eliminated and a gap remains. The X-rays are turned off during the eliminated or negative phase. With only the positive phase remaining, the electric current is direct only, or DC. The X-rays are pulsating on, off, and so forth at a rate of 60 pulses per second.
With full-wave rectification, employing 4 diodes in the circuit, the current can be redirected during the negative half of the electric cycle so that the current will flow in the same direction during the negative half of the electric cycle so that the current will flow in the same direction during both the positive and negative halves of the cycle. This process is called full-wave rectification because it utilizes the entire electric cycle for X-ray production. The negative impulses are made positive during full-wave rectification rather than being eliminated like in half-wave. The pulsed X-ray output of a full-wave rectified machine occurs 120 times each second compared with 60 times a second for half-wave rectification. This results in a doubling of the X-ray output. The waveform of full-wave rectified current is shown here. Note there are twice as many impulses in the cycle compared with half-wave. All modern general-purpose X-ray machines are full-wave rectified. The main advantage of full-wave rectification is that the exposure time can be cut in half because of the doubling in X-ray output compared with half-wave rectification.
Now let's talk about different types of generators. Single-phase X-ray generators are powered by a single source of AC current. Single-phase generators produce a pulsating current that alternates from positive to negative during each electric cycle. Therefore, single-phase current results in a pulsating X-ray beam. The 3 voltage waveforms and rectifications described earlier were produced by single-phase electric power. In single-phase current with full-wave rectification, There are 120 pulses of electricity per second that create 120 pulses of X-rays per second. Single-phase generators are considered the lowest power and most basic X-ray machines. These are also the least expensive, which makes them a popular choice in small clinics and physician offices. Three-phase X-ray generators are powered by three separate sources of AC current at the same time. A more constant and efficient voltage source is provided by a three-phase power supply. AC is generated in three overlapping cycles that produces the waveform. When this current is rectified, its waveform has the appearance of a ripple, with no real low points. Remember, single-phase has 120 pulses per second, so in three-phase current with full-wave rectification, there are 360 pulses of electricity per second that create 360 pulses of X-rays per second.
High-frequency, HF, X-ray generators are the most common generators used today. They produce X-rays much more efficiently than single-phase or three-phase generators. A single source of AC current, similar to single-phase, is used to power the generator. The primary function that occurs in the complex HF circuitry is that the 60 Hz full-wave rectified circuit is converted to a significantly higher frequency of about 6,000 Hz for most general-use generators. The highest powered HF units can convert the frequency to as high as 100,000 Hz. Inverter circuits bring the frequency up to the high level, and several layers of smoothing capacitors assist in creating the high-frequency current. The inverter circuit changes the wave-like current into a square pulse. High-frequency generators produce a near-constant voltage waveform, which results in even less exposure time compared with three-phase. They produce the greatest amount of X-rays for the same exposure technique. The very high frequency produced in an HF generator can sometimes be heard as a singing sound. High-frequency generators are not only used because of their efficient X-ray production, but also because their overall size is smaller. The high-voltage step-up transformer tank is about 1/10 the size of that in a three-phase generator because it produces X-rays more efficiently at high frequencies. This reduces the overall cost of the system.
Wow, that was a lot to go over. Thank you for learning all about the X-ray circuit with us. Make sure you go over the notes section of this lesson and rewatch this video again to become familiar with the X-ray circuit. Even though there may be few exam questions on this particular topic, it is useful to understand the complicated circuitry involved. With repetition, it will become easier to understand. Be familiar with what is required when producing X-rays that are efficient and portable enough for everyday clinical use.
Have a great day and happy studying!